Aluminum and their alloys are widely used in transportation, mobile communications, and aerospace. So high-strength 7000 aluminum alloys with the element of aluminum, zinc, magnesium, and copper are widely used in aerospace due to their high strength, low mass density, and abundance. However, these alloys are subject to hydrogen embrittlement. Unlike to steels, these mechanisms are not well understood. Regarding the questions of where the hydrogen is located in the microstructure and how do such traps facilitate embrittlement, in our study, we try to answer these questions. As we all know, hydrogen is the smallest and the lightest of all elements, and it has a low solubility in aluminum alloys. This makes it very challenging to detect hydrogen in aluminum alloys. Thus, to understand how hydrogen interacts with the microstructure in aluminum alloys. For this, we use the latest developments in cryogenic-transfer tomography that developed at MPIE. We firstly electrochemically charged our sample through the hydrogen isotope of deuterium. By using deuterium, we could avoid several hydrogen artifacts from the environment. After hydrogen charging, we quickly transfer our sample to the cryogenic plasma focused ion beam and prepare the sample, and then we transfer our sample to the cryogenic-transfer tomography to measure it. Here is how antiprobe works, is that we use a high voltage to remove the atoms from the surface of the sample and get collected by the detector. And through the three-dimensional reconstruction, we could see the hydrogen interaction with microstructure in three-dimensional. By using this method, we could now answer the question how hydrogen interacts with microstructure in aluminum alloys. We see that hydrogen has a big influence on the mechanical properties of high-strength 7000 aluminum alloys, with 50% ductility loss. By looking at the fracture surface, we see that the crack mainly propagates along ground boundaries. By using the cryogenic-transfer antiprobe tomography, we were able to see that hydrogen is located inside the big particles and at ground boundaries compared to the bulk. But the crack is mainly occur at ground boundaries. Why this happens? So we turn to simulation and we see that hydrogen, when it's located at ground boundaries, it is attracted by the high energy regions which cause the materials failure. While when it at particles, it worked as hydrogen traps which hinders crack propagation. Now we are able to see that hydrogen is located at the particles and the ground boundaries, but when it's located at the ground boundary, it's a weakening point of the material. We know that hydrogen can enter the material and has an embrittling effect on the mechanical properties. Now we are able to show the locations of hydrogen in the microstructure and know the weak points of ground boundaries when hydrogen is located together with magnesium. So these findings can provide better understanding of the hydrogen embrittlement behavior in high-strength aluminum alloys and provide possible strategies for improving the hydrogen embrittlement resistance of this material. These findings give us some solutions to improve hydrogen embrittlement resistance. Basically, there are two strategies. The first strategy is to use the particles that can trap hydrogen inside the bulk material. For this, we need to manipulate the particle size and the volume fraction of the particles while maintaining the material's strength. The other solution is that to eliminate magnesium content at the ground boundary, because we see that when magnesium is paired with hydrogen, it causes embrittlement behavior. For this, we can adjust the alloy composition and properly design the heat treatment to control the magnesium content at the ground boundaries. These are the next steps for me to improve the hydrogen embrittlement and the sustainability of the high-strength aluminum alloys.